Welcome to a continuation of our discussion on vectors. Today we're going to be doing a 2D vector example, and it's going to be an example of displacement. We have a missing aircraft, and it is spotted sometime after it has gone missing from the hangar, going some speed and a direction. We want to know how far east is the plane from the airport which it departed, and how far north is it from the airport from which it departed. To do this, we can draw a picture. I'll set the coordinate system just using the cardinal directions. If we call the position vector of the plane R, and it begins at the origin, which is where the airport is located, we have a sufficient coordinate system to work this problem out. So we know that it was spotted 316 kilometers away. So this comes from the north component here and the eastward component here. This indicates that is the distance that the plane is eastward and northward of the airport. One issue that we have is that nobody knows at what time the airplane thief departed. So we have information about the mass and the thrust generated, and we're also going to assume constant acceleration. This will allow us to employ our kinematic equations. To get a better picture of what's going on, I can take a look at my initial diagram here, and I can see right away that y of t is equal to r of t times cosine 30. Right, so I can actually just analyze the path, and let's draw a picture showing like the typical altitude profile roughly of some aircraft. I'm no expert at this, however, I imagine it's something like this, right? Disregard the altitude change. Assuming constant acceleration will allow us to employ our kinematic equations of motion. So we're going to make a couple of assumptions and observations. The northward position at time equals 0 is 0. And similarly, the velocity at time equals 0 is 0, meaning we're starting at rest. And from our initial diagram, we can just see that y of t equals r of t times cosine of 30 degrees. And that's equivalent to, so basically x of t is just a scaled version of r of t. It's just the eastward component of r of t, right? We need to calculate the total time. So we know that r of t is the direction of the aircraft path. And if I want to just kind of see the aircraft path in terms of the vector r of t, we have some plane here. And then our initial conditions are this. We know that when the aircraft was sighted, however, the speed of the aircraft was calculated to be 167 meters per second. We need to determine what time the plane was stolen. So the first thing we need to do is we need to calculate the total time interval as the aircraft approaches this speed 167 meters per second. Notice it doesn't say that the aircraft reaches 167 meters per second at the location at which the aircraft was sighted. It just says that it's measured at that location to be 167 meters per second. So if we assume that the plane got up to this cruising altitude of 167 meters per second and then chose to cruise at a constant velocity, which is much more likely, then we'll have two different time intervals for which we can analyze these equations of motion. By drawing a picture of the flight path, we can get a much better picture of what is happening. I have reduced this to a one-dimensional situation. So we know that force equals mass times acceleration. But the best way to go about this here is to draw a free body diagram. We are going to neglect air resistance. This problem is simply to show the mechanics of how the equations of kinematics play into the kinetic equations of force. And so in a typical aircraft free body diagram, when we're analyzing the motion in flight, you have a lift force that is balanced by the weight of the aircraft. This keeps the aircraft stable in the vertical direction. So we can actually say that the net force in the y direction equals W minus L equals 0, indicating that the weight equals the lift. Now, since we're going to neglect air resistance, typically we would have some vector here that was pushing back on the plane called air drag, and then we would have the thrust of the engine pushing the aircraft forward called T. Because we're neglecting the air drag, we're saying that this is 0 and that the thrust force is the only thing acting in the x direction. The sum of the forces in the x direction, according to our free body diagram, is going to be the mass of the aircraft times the acceleration in the x direction, which is constant, mind you. The acceleration is constant, so we can employ our kinematic equations after we know what the acceleration is. The sum of the forces in the x direction is just the thrust force, right? So that means that AX equals the thrust force divided by the mass of the aircraft. And this makes sense. The object, the acceleration that the object has is just a ratio of the amount of force per mass that is exerted on the object. That will determine how fast an object accelerates, and we see this in everyday life all the time. Let's continue plugging in. We said that the thrust force in the problem statement is 9.8 times 10 to the 3 newtons, or 9.8 kilonewtons. The mass of the aircraft is known to be 6,800 kilograms. Okay, so now here we have the constant value for our acceleration. We can start using our kinematic equations of motion to solve for the time required for this aircraft to reach 167 meters per second. Remember, it's not how long it takes to get to the destination. We're going to be getting the amount of distance and the amount of time it takes to reach the top speed first. And then from there, in our second time interval, we'll have a 0 acceleration case where the velocity is constant, and we can pretty straightforward analyze the amount of time for that interval and then sum them both together. So let's just do it real quick. Okay, so we have a time of 219 seconds. What we need to find now is the distance that was traveled in that 219 seconds. And so I'm going to apply the kinematic equation for displacement in the r direction. And we can do the y direction and then convert it using our conversion factor that we had earlier. So I'll just do that. So x is 0, or y is 0, 0, and initial velocity is 0. We're starting from rest. This is the only surviving term. This gives us 34,700 meters. Okay, so what this means is that it took 219 seconds and a distance of 34.7 kilometers to reach this top speed of 167 meters per second. So we know the amount of time that has passed now, and we also, for the first time interval, and we know how much distance they have gone. Well, let's use the amount of distance along the r vector, right? So right now this is for along the y vector, but we said that y of t is equal to r of t times the cosine of 30 or times the square root of 3 over 2. And since we have that, we can actually just figure out that r of t. So we're interested in looking at r of t because that's the vector that is the flight path of the aircraft. Y of t is just the vertical component, or the northward component, right? So r of t is just going to be and so we're left with a distance of 40.1 kilometers along the flight path that it has taken from the airport. For the second time interval, we discussed that the peak speed has been reached, and for the rest of the journey until the aircraft is sighted, the acceleration will be 0 because the velocity is constant, right? So we have this constant velocity equaling 167 meters per second. The amount of distance that has passed, 40.1 kilometers. It was spotted 316 kilometers in, so that means that the remaining distance that we have is 316 kilometers minus 40.1 kilometers, and I end up getting 275.9 kilometers remaining. Well, if I'm at constant velocity, acceleration is therefore 0, then what I have here is that this change in the time interval is just equal to the distance remaining divided by this constant velocity. And here, S is equal to this 275, and VC is the 167 meters per second, obviously, leading to our second time interval being 275.9 kilometers. Let's convert back to meters. And we end up with a value of 1,684.43 seconds. We'll just chop off the last digits there. And so this is for the second time interval. The first one was 219 seconds, right? This is going to put me at 1,903 seconds. You probably want to think about this in terms of minutes, though. So we're going to say if there's 60 seconds per 1 minute. This is our unit fraction. We talked about this in another video. And this equals 31 minutes. Well, 31.72 minutes. Which is basically like 31 minutes and 45 seconds. Okay. Now, the plane went missing at 12:36 p.m. And so if we subtract 31 minutes and 45 seconds, we end up getting about 12:04, right? So now they know how far back to search the surveillance to catch the thief in the act and make an insurance claim. Okay, so that'll wrap it up for this video. Thank you guys for viewing. Please like and subscribe. Okay, so that will wrap this video up. If you have any questions or need me to clarify anything, please leave it in the comments. Also, if there's anything you would like to request I cover in the future, I would be happy to oblige. Please like and subscribe. Thank you for viewing. Have a wonderful day.